If you're following my video lessons in order, then the last video you just saw showed a Crookes radiometer. Some people have argued that the Crookes radiometer rotates because of photon momentum and radiation pressure, but it's clear that it's actually a thermal phenomenon. If it were based on radiation pressure or photon momentum, what would happen is when light is incident, then photons would hit the white side and they'd also hit the black side. But when they hit the white side, the photons hit and bounce back the other direction because white reflects. And it's a greater change in momentum when an object hits and bounces off, as opposed to what happens on the black side. When the light hits the black side of these vanes, it hits and then it just sticks. And so with greater change in momentum on the white side, it should spin in this direction. But it turns out when the Crookes radiometer is illuminated, it actually spins in this direction. And that has to do with the fact that the blacks, because it absorbs the radiation, it heats up, the air around it expands, and by Newton's third law, if the black vanes push backwards on the air, then the air pushes forward on the black vane and it rotates in that direction. But just because the radiometer doesn't operate off of photon momentum doesn't mean that photon momentum is not real, or radiation pressure. These are two interchangeable phrases, roughly. So photons don't have any mass, but they do have momentum. And when photons collide with a surface, meaning when light strikes a surface, we've been treating light as a wave. We say that the electric field oscillates according to the formula E equals E maximum times cosine of kx minus omega t, maybe oscillating on the y-axis, so we can multiply by j hat. Magnetic field is also oscillating. And it oscillates perpendicular to the electric field. And so clearly we're treating light as a wave. But light has a dual nature. It's both wave and particle. We say light displays wave-particle duality. So when treating light like a particle, we call it a photon. And we say that the photons of light either hit and stick, or they hit and they bounce off. And so if they have momentum, despite the fact that they don't have any mass, then they have the ability to exert a force across the surface area of a material when they collide with it. So if photons have momentum, then they must exert a sort of pressure on the surface of the material that they collide with. So let's come up with an expression for radiation pressure. Pressure is equal to force per unit area. It's measured in newtons per square meter, and we call 1 Newton per square meter 1 Pascal. Intensity is equal to power divided by area, but power is force multiplied by velocity. So intensity is force times velocity over area. We can write it this way. We can kind of reassociate these terms and say intensity is equal to force over area times velocity, which means intensity would be equal to pressure times velocity. That would imply that pressure is equal to intensity over velocity. Well, the velocity or speed of light is c, 3 times 10 to the 8th meters per second. So we can say radiation pressure, let's be careful, let's use capital P for power and lowercase p for pressure. So that's why I wrote it out as power and pressure as opposed to putting symbols in. It'd be easy to confuse a capital P with a lowercase p. So radiation pressure, P P is equal to I over C. Actually, that's the radiation pressure for a perfect absorber, for a black body. So when electromagnetic radiation hits and gets absorbed by a dark material, then the radiation pressure associated is the intensity divided by speed of light. If the radiation is incident on a perfect reflector, and the radiation is reflected back the other way, and you would expect twice the change in momentum and therefore twice the pressure, and that's exactly the case. Radiation pressure is 2I over C in the case of perfect reflection. So we've got an equation for perfect absorption versus perfect reflection. In both cases, it has to do with intensity and speed of light. So I'll conclude this unit of study 5.3 on electromagnetic radiation with some example problems, and you can put into practice these equations that we've been deriving along the way.